I think I can start recording today's lecture then. And as usual, we will go through last time, and then we will complete our overview of maps. I've been a little bit slower this year than the last years because, of course, this is a new mode of teaching, which I'm not entirely comfortable with, probably. So I'm going a little bit slower in explaining, in answering questions and everything. And but also because I realized last year that not everyone did properly understand this part of the course. And I think it's really, really, really important to really understand it deeply, because it's a very simple mathematics behind it. It's not complicated multidimensional analysis or anything like that. It's just derivatives and basic algebra. Really, it's not even algebra at this point. It's just calculus, like high school calculus even. So the instruments are really, really simple, but it's also risky because you are kind of tend to stay in the shallow understanding of this thing. You say, yeah, this is a very simple part of the course. I kind of grasp it. That's okay. It's not that I have to use it, but actually this is probably the most crucial thing about scales. It was in the last two lectures. So if you really deeply understand the last two lectures, then everything else in the course will be a walk in the park, maybe with some more or less mathematics, depending on how what exams have you taken before this, how theoretical are you in your background. It would be more or less easy, the details, but the physics, it's everything is inside these first two lectures. So if you really have an intuition of what happens and why, then it's really going to help you in this course. So please, please, please do questions if you have, if you don't have any clear anything in this part. It's fine if we go a little bit slower here, because this will really help us afterwards. And also do the exercises. So I know that some of you did the exercises, that there was a good participation of yesterday to the exercise session, but you really, really should do the exercises, especially for this first, because then you really, this is what the exercise is all about. It's your self-evaluation on how you understand the theory behind the exercises. And if you get it, if you really can do the exercise in a breeze, then this would be really fun the rest of the course. Otherwise, you will struggle and will be less fun. So, okay. Having said that, do you have any further questions? So, if not, we will continue on our overview of maps, and then hopefully we will start fractals, maybe in the second hours. That is one of the favorite part of the course for many, many people. So let's share my screen as soon as I can fix the mouse. Share screen, iPad, and then screen. Perfect. Okay. So first lecture we did review, we did define our maps and the population dynamics and everything. And we find out that a map can be, or a fixed point is when the map is, the result of the map is fixed and stay fixed for a long, long time. So let's do it like this. So if the results of the map stay fixed for a long, long time, forever, then that is a fixed point, and one can study the stability of the fixed point. So if you are a little bit away of the fixed point, will you reach eventually the fixed point, or will you be drawn away from the fixed point? And this really depends on the derivative at the fixed point, or of any other point for that matter. And then you can study the logistic function and find out that there are several regimes to this very, very simple equation. And I lost the chat, so here is the chat. Okay, so there are very, very different regimes for these very, very simple equations. equation, and it can be reach it. It can die off asymptotically if this proportionality factor, the multiplication factor, is smaller than 1, or it can reach the fixed point asymptotically, making this logistic function that you are all very familiar with. It grows exponentially at the very beginning and then exponentially reaches the fixed point. But then if the R is larger than 2, what happens is that it will start to oscillate around the fixed point. So it will not be the logistic function, very easy, very smooth behavior, but will oscillate with a dampening oscillation around the fixed point, reaching still the fixed point asymptotically, but oscillating around it. And if the R is greater than 3, then what you have is that your fixed point splits in 2, and then you have this up and down oscillating solution between two solutions. And this can be studied as a fixed point of the second return map. And then what happens is that the more you increase the R, the more you increase this number of fixed points for the nth return map. And therefore, you can write this as a bifurcation graph. And then you can study it analytically, defining the Lyapunov exponent. And this is all pretty standard, and it's basically all the pure theory background that we need right now. Now, what we are left in the curriculum in this part to study is this is the tent map. Okay, so the tent map will be a sort of draw. Yes. Okay. So the tent map is another example. So we established the logistic map, which is a very familiar and important example. But it's an example that is even more simple and still has a fairly complicated behavior, even though not as rich as a fixed map, is the tent map. So it is a map that it's done like this. It has two regimes. One like this, when x is between 0 and 1/2, and then one like this, when x, x is between 1/2 and 1. Okay, so what happens in this case is that so this is our usual way of writing the maps, where with I have to get used to this system once again. So this is xj plus 1. This is how maps are done. I hope you all remember it very well by now. So the way we design maps usually is like this, designing the function that defines the map that also correspond to seeing for given xj what happens at the next iteration at xj plus 1. The tent map behaves in a way that is a linear. So it's linear for between 0 and 1/2. It's linear in both cases, but it's linearly growing between 0 and 1/2 and linearly decreasing between 1/2 and 1. So this defines it like this. It grows in this way, and then it has the second segment, and it's equal to 0 here, and when xj is equal to 1, xj plus 1 is equal to 0, and when xj is equal to 1/2, then xj plus 1 is equal to 1. Okay, so this is an even simpler type of map respect to the logistic map, but it kind of has the same features. If you remember, another thing that we used to do is to draw the secant here, that this is the line where xj plus 1 is equal to xj, and this helps us in kind of seeing what happens for things. Okay, so now, why do I do this? Because it's a very simple map. It's one of the few maps where the behavior can basically completely be studied analytically. In the logistic map, we have this rich behavior, but basically the only way we can properly study this rich behavior and kind of study the chaotic regime especially is by seeing the numerical solution of these of the solutions of the map, of this first sector map. In the 10th map, this comes way easier because maybe you notice that this has a very peculiar property, that the derivative of this map, that, as you remember, teaches us a lot about the stability of our system, is basically just either 2 or minus 2. 2 when you are between 0 and 1/2, and minus 2 when you are between 1/2 and 1. Okay, so this is very, very easy, very simple. And now we can study the Lyapunov exponent. So Lyapunov exponent for the 10th map, that's very easy to do, because if you remember the Lyapunov exponent is given by the average of the logarithm of the derivatives, of the absolute value of the derivative. So if I take n points, so I iterate, and you know, as usual, what happens is that you start from a given point, and then you will go around, and this will go up and down like this, and you will have different solutions. Okay, maybe I've done too much. Okay, so you will have different solution, and then you take all of these solution and you average the value of the derivative at each of the solution. But so this is numerically relatively challenging. I mean, you cannot do this for the logistic map because the value of the derivative will be different at each and every point. So this is not feasible. You can do some averaging, some general studies, but for a realistic trajectory, for a specific trajectory, this is definitely not feasible. But in this case, this is very much feasible, because this is just the average of the logarithm of the derivative of the absolute value of the derivative of x. Yeah, if I put usually the sum goes from, for I, that goes from 0 to a given value, and this is xi. So if I follow a trajectory, but then the absolute value of the derivative in this specific case is always 2. So this is given by 1 over n by the sum, again, of the logarithm of absolute value. The absolute value is always 2. So this is the sum n times. So this simplifies with the n. And what you are left is that the Lyapunov exponent in this case is simply the logarithm, the natural logarithm of 2, which is 0.69, I wrote in my notes. I hope it's correct. But as you can see, it's larger than 1. So this extremely simple map has a positive Lyapunov exponent, as a non-periodic behavior, because it has some periodic solutions. In particular, I think you can see one periodic trajectory, or semi-periodic. I mean, it can go, if you start from, if you reach 1/2, then what will happen is that from 1/2 it will go to 1, and from 1 it will go to 0, and then it will stay there forever. But also there will be some solution at some point on this line that will go between these two solutions forever, oscillating here. So you just have to find the right numbers. But apart from these very specific trajectories, a random point, if you start from a whatever point that is not periodic, then you will have a non-periodic trajectory and will stay that way for a very long time, if not forever. And since there is basically no periodic cycle in this map, what it means is that the system is chaotic. Okay? Questions? No? So I accelerated a lot the way I talk, and I also said something that is not entirely true, and I don't think any of you realized. So this is not completely an April fish, only partially. So what did I say that is not correct in my last 5 minutes, 3 minutes? Does anyone has any idea? Do you want to write it in the chat? You say the system is chaotic, and you think it's not correct, Kim?
Yes, because you said that the system can be completely understood analytically.
Mm-hmm.
And that doesn't sound like a chaotic system to me.
Okay, that's a good point, but actually the system is chaotic because. So, any other ideas on aperiodicity? Doesn't have to imply chaos. That's very good. That's a very good, really good points. So, first of all, the system can be understood analytically, so it cannot be chaotic. So that's a hard one. That's really, I can understand the confusion because it's really hard to kind of have a specific grasp on what type of system is chaotic. For the map, we have a very simple solution, a very simple definition of chaos for these one-dimensional maps. That is, if the map is aperiodic and has a positive Lyapunov exponent, then it's chaotic. So these are only two necessary conditions, and both of them are sufficient for the definition of chaotic. So it's true that not all aperiodic systems are chaotic. Especially, we will see later on that there are regimes which are called quasi-periodic, for example, which are not chaotic at all, are very regular, but are not periodic. But in the one-dimensional map, aperiodicity also doesn't have to imply chaos, because it can be that there is a negative Lyapunov exponent. So the system is aperiodic in such a way that all solutions converge to the same aperiodic cycle, in a sense. It's not a cycle because it's aperiodic, but it converges to the same aperiodic trajectory. And so that's a very good point. But if the Lyapunov exponent is positive, then there is not a single aperiodic trajectory that all the solutions converge to, because the Lyapunov exponent is chaotic, so solutions diverge. And what I said, well, I don't know if that's what I said, because I said it very fast. Now nobody picked it up, and actually you make a very interesting point about aperiodicity. So this system is aperiodic, does not have any periodic solution. I thought the time I spoke, and I said that it has two periodic solutions, but no. So I cannot find 2 points that jumps between those two forever in these type of maps. And that you can also demonstrate analytically. Now, this system is chaotic, even though it can be understood analytically and can be followed. But again, the trajectory of two given solutions are not super easy to, are still analytic. I mean, in a sense, let's say, in a sense, all maps, all, not all maps, but all analytical maps, like both the logistic map, the tent map, and every other map that you can write in a simple, neat equation are all analytical. And the system can, in principle, be studied analytically. In this case, it's very simple to study it. But even the logistic map, you can analytically study the behavior of the system if you use computational tools. So tools for symbolic computing, you know, for example, Mathematica, that you write an equation and the system can iterate a given equation. For example, if you take either the tent map or the logistic map, and then ask what's the solution for a given n, Mathematica, that was written by Stephen Wolfram, the guy that I talked about at the very beginning in my April Fool joke. So Mathematica, what you can do is derive an analytic formula for the calculation of the solution at the I iteration. And in a sense, a generalized program in Mathematica can be seen, it is an algorithm that describes the general system and the general features of the logistic map. In fact, I talked about last time of universality, and we will see it also today a little bit better, but many formal demonstrations of the properties of one-dimensional maps have been done in this way, are mathematically rigorous computational demonstration, but that are based not on a pen and paper type of mathematics, and not even in a numerical type of mathematics, but in a computational kind of demonstration that is done in a way so that the computer handles the symbols already, no? So you can demonstrate things using a computational, analytical things using a computational program without ever inserting numbers there, because the program can iterate your symbols and can find solution to your symbols. Many demonstrations in higher mathematics that are done today in calculus, actually, specifically, are often done nowadays with computers, are computational demonstration that demonstrate analytically, but it's the computer that demonstrates, not the guy with pen and paper, because for a guy, it will take more than a lifetime to kind of write down all the solutions from 0 to 5,000 and then kind of extrapolate the general behavior there. While for a computer, it takes a few minutes, and then you can kind of make general conclusion from there. So that's a whole branch of mathematics, the symbolic management. So that's not a big, that's not a hurdle for chaotic system. And especially with this map, this is chaotic precisely because it does not have any periodic solution. If the tent map were to have a periodic solution, what would happen then is that after an infinite number of iterations, after many iterations, sooner or later, a chaotic system is generally also ergodic, and this is another thing that we will see in the course. So it explores all the possible solutions, and therefore it would land on the solution that is periodic. So we start to jump back and forth and finalize its periodic behavior. So it will not be chaotic anymore. But if there are no periodic cycles within a map, then even though these map is very simple to the point that we can study it analytically, it can still have chaotic behavior. So any questions? Was a long rant. I hope it was relatively clear. Any feedback? No? Okay. I hope you're still there. So, okay. So, in fact, one of the things that was demonstrated using this type of symbolic handling is the fact that this state map is basically equivalent to the logistic map. All maps that behave in this way, that start from 0, then go up, have a maximum, and go down to 1 smoothly without any, the derivative is not smooth, but the function itself is smooth, does not have any discontinuities. I mean, in some mathematical sense, it's smooth. So if they go like this without discontinuities, then they all have the same behavior. So this state map still has the same behavior as the logistic map, in the sense that still have chaotic features. And all map of this class can be studied by going into the definition of a simpler kind of map and of the logistic map. This is why it's so powerful talking about maps, one-dimensional maps, and logistic map, because basically every kind of behavior that you will find in a physical system, if it's not completely crazy, can be reduced to a smooth map in some sense. And the smooth map can be connected to the logistic map and its property. So we'll have a very similar, basically the same bifurcation diagrams, for example. Both the tent map, the logistic map, and any other kind of map that is continuous and goes from 0 to 1 in a smooth way, then can be reduced to the logistic map and has the same features, and enjoy this set of behavior that we've seen. And that's quite fun. Okay, so now let's consider the state map. Why did I explain to you this simple state map? Not only to make me go around in this way, but because it can be understood in a way that is a little bit simpler than the logistic map, because of this doubling property. And basically, let's see, it's within the book, it's in page, I forgot to open the PDF, but I think it should be, are you still alive? Do you still hear me? Am I disconnected? Or okay, yes, good. So that's Patrick makes very nice questions. Chaotic system end up exploring all points, and so a map with a periodic solution will end up in the periodic solution. But this map have a stable point. Won't it end up there? And it does no longer chaotic, or I'm missing something fundamental. You are right, in a sense. The difference, I mean, the point is that while chaotic systems are ergodic, if you have a you end up exploring everything, and you risk to encounter the stable point. But the stable point is basically, well, it's not basically, apart from 0, then the stable point is really only one point. And there is an infinite amount of points here. So it will take an infinite amount of time to land on the stable point. So at any given iteration, then you will have to wait basically an infinite amount of time to reach the stable point. But if you have periodic solution, it means that there is some sort of regularity in your map. We will see it also. This is related to something that we will see later in the course that has to do with some very fundamental theorem, the Poincaré theorem. The screen sharing is paused. Is it? I'm not doing anything, sorry. I'm just talking. So, no, it's not paused. Okay. So I was saying, I did write this, no? So you have a single point here. So we run across all the points, but you have just one in an infinite number of points possibility of touching exactly this point. And if you get close here, you will not be attracted to this stable point. In fact, you will be repulsed precisely because of the Lyapunov exponent, okay? But if you have a periodic solution, then what means is that you have some stability over your system. And we will see it in the later on in the context of what is called a Poincaré map, that if you start to have periodic solution, you will start to gravitate in a way around these periodic points. You don't necessarily, because you give something like pi4 initial point in it, may not explore integers. That's possible. I never thought of this. If you give an irrational number there, or a non-computational number, you might be stuck in some subset. So, but in general, chaotic systems are ergodic. So they explore all regions. Let's say it's not an analytical point. Well, analytically is defined through the Lebesgue measure. So if you're familiar with the advanced calculus, then it is related to Lebesgue measure. So it will explore all points apart from a null Lebesgue measure set. But that's a good question. I will have to think about it, because you make a good point about subsets which are completely excluded, and that's interesting. In this case, I mean, you don't explore integers, but in a sense, the integers here in this map specifically is just 0 and 1. But I think it might be possible. So it does not apply to these specific examples, but I think it might be possible to have something like you say, and it's an interesting point. Okay. Other questions? That's good discussion that we are having here. I mean, I'm the only one talking, but you are writing, so that's fine. Should I go on? It's already good point there. Okay. So let us go on. And one thing that is interesting to study with the tent map is the fact that you have a behavior which is called well, it's called in several ways, but it's described as the stretch and fold behavior. Because if we take the tent map like here, and then we start with two very similar points. So let's draw it in green, shall we? So we start with two similar points here. So do you see the screen? Is it still on, the screen sharing? Yes. Okay, so you see these 2 points. You take two very close points, and then you project them onto a line of numbers. So if you take these 2 points, basically you reach that correspond of taking xj's that are like this. Now, what happens if you take these 2 points? The next iteration, what happens is that they will have to handle a little bit of colors. They will have stretched because you have a proportionality factor 2. So if this point is 0.1 and 0.2, let's say, since the 10th map is done like here at the beginning, just 2x, and xj1, this will be, so let's suppose this is 0.1, 0.2. Here it will be 0.2, 0.4. So it will double. So the doubling on this line of numbers will be represented in this way. So let's take this and then a double here. So if it's 0.1, then these 2 points will be the same. But I don't want, okay, let's do like this. So the first point will move here, and the second point will move here. So this is the first point, and this is the second point. Okay, then we go another iteration. And what happens is that these 2 points well, these are not 0.1 and 0.2 eventually, but these 2 points will arrive and be corresponding to 0.4 and 0.8. Now, what happens is that then, let's keep the purple here. So this will go 0.4 and 0.8. So this is 1 and this is 2. While doing this is equivalent as taking this line and stretching it in a sense. What they're doing here is taking these 2 points, is corresponding to taking these 2 points and stretching it into a line that is doubly long or 3 times as long. Okay, so this line will be double and here it will be triple. Okay, and these 2 points will kind of stretch to be these points and then these points. Is it clear how am I designing this? Yes, because without showing it by hand and making it a little bit more dynamical is a little bit more difficult to draw it. Yeah, very clear. Okay. So basically,
sorry, I have a question.
Yes.
So are the different lines each iteration then?
Yes. So
all right, thank you.
This is kind of iteration 1. Well, this is all iteration actually, because I wrote iteration 1, 2, and 3. But the green here is iteration 1, the green here is iteration 2, and the green here is iteration 3. Okay? So if we design with the green, then it would be like 1, 2, 3. It would be like, if you look at my screen, I don't know if you see my image, right? Also, a little bit in a little, but so it's, you take it length 1, and then what you do is you stretch it twice, and you get the same, the points that you have there, like an elastic. I have an elastic here, maybe. Okay. No, it's not an elastic. But if you have an elastic, you draw the 2 points and you draw it with a pen. This is what I do in the lecture usually. I draw it with 2 points with a pen and then I stretch it. But now something funny happens, because now I have to find another nice color. Let's use it light. What happens here is that this is 0.8 and will be higher than this kink that you have in the function. So the new solution will be smaller than 0.8. I don't want to calculate, but this will be smaller than 0.8. And this other solution will be then 0.8. In this case, because I've been a little bit stupid in taking them one double the other, then what happens is that the second point will follow the first one. But as you can see, the first one is doing like this. And this will correspond of drawing it again into a line. Sorry, yeah. So this is, the iteration 3 is not length 3 because it doubles the iteration 2. So it will be length 4. So but this is still iteration 3. Okay. And then what I will do is to take this and double it once again. Now it's becoming a little bit difficult. But the point is that if I double it, the one below is not going to go up, but it's going back actually. So instead of doubling in this way, I double it in that way. It's not now. It's not my best drawing. Let's try to do this. No, but okay. Tack, tack. Okay, this is why it's a little bit longer to explain things in this way instead of backward. So what happens is that the doubling of this will go over and go on the other side because it will go back. So it's like, this is still doubled, but it's like that is being folded, okay? And this is in the same spot that was the one before. Okay? Is it remotely clear? So if I do it as a stretch, an elastic, I draw the 2 points, and then I can do it case by case. But after the second, I will stretch it once, and then the second time I will fold it, and then I will stretch the folding again, and I will stretch the one that is folded. I will stretch it, and then I will fold it again. So each iteration, in the one iteration you stretch it, in the second iteration is as if you are folding it. Because the one that goes over the middle actually comes back. So this is how Danish pastry is baked. So you should be familiar. And I have a video for after the break about Danish pastry, or I will find it. I don't have it right now, but I can find it, and then it would be maybe a little bit more clear. But that principle is actually also a property of chaos. The fact that you have a topology, a geometry, which is entirely non-trivial. Okay? Is it okay? You can discuss it in the break. One thing that I want to repeat is this universality. So now what I want to do is to share not the screen, but my PowerPoint. Okay. So this is my favorite GIF, and it's about the sensitivity to initial condition. This fact of stretching and folding is actually what determines the completely different behavior, the sensitivity to initial condition. Because if one point ends up being folded respect to another that is not, then the evolution in the future will be very, very different, because they will be on different sides of the folding. And this sensitivity to initial condition can be seen in this way. This is a pendulum, A triple pendulum, this is a slightly different system, is continuum, it's not mapped, but these represent very well the sensitivity to initial condition. These are many, many pendulums that are initiated at slightly different initial conditions, and then let evolve with the equation of this triple pendulum. And then for a while it go on like it is as usual, but then after a while, then you have this chaos. The solutions diverge and you have chaos. Last thing that I want to mention about maps, and then I think we can go to fractal and we can go break, and then you can have all sorts of questions about map, but then we will close this chapter and we will come back again, because as I say, this is a really important and key way of reading chaotic behavior, the maps. It's the hallmark of chaos, maps. So another thing is this universality. So I've shown you these logistic maps. So this was the bifurcation. And on the book, you have the bifurcation diagram for the 10th map, which is exactly the same. It doesn't change at all. It has exactly the same structure. It has different fixed points, but this is another story. So it can be squished a little bit, but it's exactly the same. You have a regime with one fixed point and a stable solution when R is very small. In the case of the 10th map, when the factor that I picked as 2 is not 2, but is smaller than 2, or smaller than 1, sorry. If the factor grows, then you have 2 stable solutions, but if the factor grows still, and it's 2 or larger, then you have this very chaotic regime. For the 10th map is 2 or larger, for this it's 3 point something, 3.6, 3.65. Then you have this chaotic regime, but then you have some stability in the middle. So this is really, really interesting that you have this stability in the middle. And this generates a lot of behavior. But the fact that this map will always look the same for whatever map that I choose, as long as it is, like I say, it has a minimum in 0, a minimum in 1, and then it's a smooth connection in between, a continuous connection in between. So the fact that this is all the same, it's really interesting. And it's a property that is called universality. The map is the same, and not only the map is the same, but the proportion between sides of the map, so from one bifurcation to the next, the proportion is always the same also. This was was something noticed by, this is also similar to what I said before. It was something that was noticed numerically first by Feigenbaum in the 70s, 72. He noticed it and published in 75, I think. But yeah, in 75 it was published, or 76. In middle of the 70s was published the discovery, the fact that the ratio between the different steps in the logistic map converge to a fixed value, which is 0.4669, and so on, for many, many types of maps. So this is for the logistic map, but not only, for all type of maps that have the same topological behavior. And convert to always the same number, and this is called Feigenbaum number. And this universality property, it's really interesting and was discovered numerically by Feigenbaum, and was later demonstrated analytically, but using these very specific tools that come from computation. So using synthetic symbol manipulation. So a demonstration that was done by a computer by means of iteration and induction proof done by the computer, but symbolically, not numerically. And this was done in the 80s by another guy called Langford, I think it was. But that's also interesting. I mean, that tells you that the numerics builds up the intuition and make you see these very general, very interesting behaviors. And then you can go back and kind of study with the mathematics that is both either analytically pen and paper, like we did during these 2 lectures and a half, or more rigorously and aided by the computer. I have also a friend that does these sort of things, that does mathematical demonstration, computer-aided mathematical demonstration of chaotic properties, of chaos theoretical properties. Okay, so this is really interesting. And this property is universal and shows the self-similarity, because if you zoom in into one of these bifurcations, you will see exactly the same behavior. And a last property of chaos is intermittency, or not of chaos, but of this kind of maps, often is intermittency. And this is done very well by one of my, something is happening to my phone. Somebody's calling me. I hope it's nobody of you. Okay, sorry. They knew that I had the pause right now, so no, it doesn't matter. So this is done in the book at page 47, if you have it under your eyes. If don't, I will have to take it here. So share this one, okay. Page 47, you see this intermittency behavior. So what you see in these sort of maps is that you have a quasi-periodic behavior for a very long while, and then you have a regime which is chaotic, and then almost like a fixed point, and then it starts again the chaos, and then again the quasi-periodic. This happens close to the 3-periodic regime, for example, in the logistic map, but it happens very often in chaotic system, and this is important for many applications. So this happens because basically what happens is that your graph gets closer and closer to the bisection line. So this is the line, and when this is touching the line, then you have a fixed point. If it's touching 2, then you have 2 fixed points that sometimes can be interpreted as 2 periodic solution. So what you have that is happening here is that as the map moves closer to this fixed point, the iteration gets more and more dense. And the more dense it becomes, the more regular is the behavior in time. So you have this 3-periodic behavior that is given by the fact that the system is nearly touching the 3 periodic points. And then if it were exactly touching, then you have exactly the periodic behavior. But if it is nearly touching, then you have 3 periodic behavior for a long while, the long while that the system bounces. Can you see my mouse cursor as well? Yes? Okay, while that it bounces, so it goes like this, and it arrives with big steps that is given by the 3 periodic behavior. And then it arrives here, and it's the one, once it is here close by, it jumps iteration by iteration, moving very, very little. As you can see here, these are many, many iterations, and many, many iterations will move very, very little. So this is what's happening here. You have this chaotic regime that is given by bouncing here in a complicated fashion, but then you get close to here and it will bounce very close by here, and it will generate system that which looks very closely to regular. So it will have 3 regimes at the end of the day. It will have a 3-periodic regime or nearly 3-periodic regime. It will have a chaotic regime, and sometimes in the middle, this will look almost like a fixed point. So it will be a stable system. And this is important in many applications, because if you look at automatic control, for example, you will have a system that behaves very nicely for a long while, but then it behaves very, very strangely, and then it's stable, and then it starts to behave like you wanted before. So this is something that you can see fairly often in automatic controls. It's something that you can see also in physical systems or biological systems. For example, this is a way that we measure heart failures. So when the heart is failing, normally it's pumping in a nicely four periodic way, because you have the two. Now my biologist friend or medical friend will be very much disappointed. I don't remember the name in English. So you have the big section of the heart below, left and right, and then the small one that just pump the blood to sustain the whole heart itself up. So you have these four regions of the heart, and they will pump blood in a periodic fashion, and they will pump the blood in a very nice periodic fashion. But if the system gets only slightly out of sync, what happens is that you can have these heart failures. This is what happens in heart failures, that you have the system goes out of sync enough so that I can stop sharing and see my face. So it goes out of sync enough so that the system starts behaving very chaotically, and the system is not synchronized anymore, and the blood is pumping in all the wrong ways, and then the heart stops. It's risk of stopping. And in the case of the heart, this is so risky that it's risk to stay stopped, not continue. And this is the heart failure, what happens in heart failure. So the heart has to be restarted. And then if you're lucky, you manage to restart its normal periodic behavior. And then you save the person. So this is in heart monitors nowadays. All these chaotic algorithms are embedded in the heart monitors, so they can kind of see the onset of these chaotic regimes that tells you that the patient is having a hard times with your heart and is risk to be heart failures. So computer problems. Okay, so I think now is a good time to pause, and we'll see together after the pause. I've been a little bit longer than expected as usual, but can we do a short break, like 7 minutes, and then be here in 14:20, and then I will make a little bit of announcement, and then we will start again, okay? Now, do you have any physics questions? You discussed among yourselves? Very short coffee break, very short discussion, and straightened up all your doubts? Yes? No other question. So if there are no other questions, I think we can all start with the argument that is one of the favorite of the students. Can you repeat what you say about all physical system being representable in a map? Ah, okay. No, it's maybe I misspoke. It's not that all physical systems can be represented by a map. Is that what I said is that all the physical system that can be represented by a map can be you can reduce it to a map that is well behaved, in a sense, that looks like the logistic map or the tent map, that is topologically invariant respect to these two maps that we have studied in detail. And that's exactly how you show that the system that you're studying, and it might be very, very complicated, it's in fact chaotic. You reduce it to a map representation. So for example, in my division, there is somebody that is studying quantum cascade laser, which is a very complicated system. Nobody knows how it works. So, but what happens is it's like an LED. It's a similar principle than an LED. It's based on bands that get excited and de-excited, and this emits light. But it's more similar. It's made like an LED, so it's a solid state device. It's made with bands, but it behaves like a laser. So it's a stimulated emission of electrons in these bands. So it's a very complicated quantum system that it's really difficult to model. But if you study the experimental properties of these quantum cascade lasers, then what you can see, what you can notice is that you can reduce some of this property in a map that looks like the logistic map. Therefore, you can reduce this very complicated system in something that you've studied, that is very simple, that you know is chaotic. So you know that this very complicated system is chaotic as well, which is something pretty amazing, because then you have an intrinsically quantum system which behaves chaotically. In a quantum system, it's not chaotic in the classical sense, usually, but this is kind of one of the few exceptions. And it's not chaotic in the classical sense because the quantum system is linear. So you live in Hilbert spaces, that is a linear vector space. So everything quantum is linear. So usually it does not show a chaotic behavior, but the synchronization of several linear systems can give rise to chaotic behavior, and this is one. So this is how you do in research. You take your data that you have that might be very complicated, and you try to reduce it to something that you know and you can model, and then you have the logistic map, and then in this way you really have demonstrated which is chaotic. It's not only by seeing data going up and down in a crazy way, because it can be random. It's quantum, so it can easily be random. But if you can reduce your data to reproduce the logistic map, then that's how you know that it's really chaotic. It is possible with a double pendulum, and we will see it that the double, triple, the pendulum can be represented in what is called the flow. So you write the linear differential equation that make up your system, your pendulum, and the linear differential equation that make up the pendulum is nonlinear because you have a sinus term. So it's, you have this trigonometric function. So if you put 2 on top, then it's highly nonlinear and you have chaos. And how you can go from that representation to a map by doing what is called a Poincaré map. And we will see that later in the course. And you can show that this map for the double pendulum goes to be similar to the logistic map, and therefore the triple pendulum is chaotic that I showed before. Okay, and double pendulum as well. So this is how usually it works. It's not that you represent it directly, but you reduce it by an operation that is called Poincaré. This is also why maps are so important, because when you are out in the real world, you see this is what you use, what you try to use. And if you have a bunch of data and you want to find out if this corresponds to some chaotic behavior or not, the way you do it is, okay, you can have a description which is given by differential equation, can be very complicated, very large, but then you have to try to find sections of this data and basically cut its behavior and see what you do with the pendulum. You see the position of the double pendulum after a period. So after a period, you see where the double pendulum, after a period of the first pendulum, for example, you see where the second pendulum is, and then after a period of the other pendulum, you see where the second pendulum is, and then by doing so, you make up a map, which is similar to the logistic map. Anyway, and that is how you find out that it's chaotic. And in more complicated cases, then you have to find out a way. This will be, I think, one of the projects, the one that will be followed by Alex, because this is exactly what Alex did at the beginning of his PhD, finding this quantum cascade laser, reducing it to a simple, finding out the parameters by which this quantum cascade laser was reproducing a logistic map, and therefore demonstrating that this is chaotic indeed. Okay. Other questions? I get carried away with all the questions, but I like it. I hope you like it too.